Hello, my name is Rohan Ray,
Hello, my name is Sashank.
and this is the ECE111 Bitcoin hashing project. So the first step of the hashing project is the SHA-256. So what the SHA-256 does is you have some arbitrary message, and the output of that message is a encryption code, which is 256 bits long, and this cannot be decoded back. So and that's very important because it increases security of messages that are being sent. And for our case, we're going to use we're going to test a 40 word, and we're going to try to encrypt that message in 256 bits. Now onto the code. So what we have is so first what we need to do is we need to store the message. This storage of message is going to be stored in the message 16. In the message, which is going to be 31 bits per in each index for 1216 index for 512 bits. So we're going to store these 512 bits 3 times because three blocks of area, because that'll make sure that we get all the contents of the messages in those. Yes. And in order to do that, what we do is we have four blocks. And first we have the state in which we initialize all of our variables and everything, which is our hashings. And then we have our block, which we begin reading data from the input message that we are given. And then we are doing compute, in which we just do the 256 hashing of each 32 bits, and then we add the hashing up to make it 256, and then we do that for each word. And then afterwards we write it in our memory. So we have a big database memory in our test bench, and we just write it over there. And that's basically what we do. And the memory is basically going to be is going to write down the 256 bits in format of 32 bits each for a total of 8 memory addresses that's going to be written from the 256 bits hashing. Currently we are at the SHA-256 stage, in which we're having inferred latch errors, and we're trying to resolve these issues. And currently what we have right now is, for efficiency, instead of using the data read variable, which stores 511 bits, we have reduced the area by storing it in a message variable, which in block, which will read the messages. If I can find it real quick, hold on. In block, yes. So in every clock cycle, right, we have an offset. The offset is basically reading each input memory address and getting the contents of the message, which is going to be a word. So in each clock cycle, we're getting an additional word for a total of 40 words, and we're reading it from the memory data, and we're storing it in message. And that's going to be yes. And message is stored 16 value, 16 bits. So message can only store 16 words. So we're going to be using it. So we are going to be repeatedly using message in every cycle, so that we can get all the 40 words possible, and we'll be able to encrypt that message. And that is the SHA-256 right now. And yeah.
So the next part of the project would be the Bitcoin hashing. And for this would be basically using the SHA-256 algorithm that we've implemented before, and basically add it to each block in the blockchain. So this is a general design as to what our objective is that we have to do for this part of the project. So we first have an input that contains 20 words. The first 19 are part of the message, and the last word is what's called a nonce, which is basically a number that's typically used only once, and it's used to authenticate a digital signature of a specific block. So this message in total is 640 bits, and this would be split into 2 different blocks. So, and both of these blocks would be passed through the SHA-256 hashing function. So the first block would be containing the first 16 words of the message. And the second block would contain the last 3 words of the message and also includes the nonce value. And once we pass it through the function, would be getting an 8-word hash. So as you can see, the reason why we compute the last 3, the reason why we compute the second block 16 times is because it contains the nonce value, and we want to iterate through each of the values from 0 to 15. And so we have 16 different nonce values in total. So once we pass it through that, would be having an 8-word hash, and each word would be having 16 different elements, which again corresponds to the nonce value. So once we have this 8-word hash with the 16 elements for each one, we would then pass it through another SHA-256 hashing function and get our final 8-word hash. So, like I mentioned before, we'd be having 16 final hashes as our final output, with each hash representing H1 to H7. And in this project, we would want to write we want to have our final output be each nonce for the first word in the hash. And the way we'd be storing this is each element would be stored to output address, and then for every element would be adding output address to the corresponding index. And some of the ways we can optimize our code is, for example, we could implement parallelism. So one way to do that is we could initialize the SHA-256 functions simultaneously because we have 2 of them. And we could also vectorize any of the for loops that we have. Or we can use vectorization instead of for loops, as well as bitwise operations, in order to increase the computation speed. And that's all there is to our project. That's all there is to the progress of our project.